Okay, so hello everyone. My name is Ruiqi from University of Edinburgh. Today, I would like to use this valuable opportunity to introduce our work on benchmark-based vitality measure of axioms and preconditions for Datalog theory repair. You may already hear about Datalog and theory repair, but feel strange about the so-called benchmark-based vitality. I will talk about this very soon. In one sentence, our research proposed a heuristic measurement, which is that benchmark-based vitality measure to quantify how vital an axiom is in a Datalog theory, so as to help select the best repair of a faulty theory among the various possible repairs. The outline of the presentation is simple. To begin with, I will introduce the background and our motivation, that is, the overproduction problem during the theory repair. Then I will lay out and talk about the prior works and highlight the distinctions between our works. Next, I will present some key details of our proposed solution, the vitality measure to the overproduction problem. At last, our empirical evaluation and experimental results, followed by our identified limitations and future work. Let's start. For the audience who are the first time to hear about theory repair, here's a very simple definition. That is to modify an existing theory so that it can be consistent with the latest observation. So just as John Keynes said, when the facts change, I change my mind. This is a famous flying bird example. Suppose that in our mind, we have such a simple theory with 6 clauses and the 3 rules are: if X is a bird, then X can fly. If a bird, then it has feather. If Y is a penguin, then it is a bird. And a more free fact: Tweety is a penguin, Polly is a bird, and Polly can fly. So far, so good. Our theory in mind is self-consistent. However, now we have some new observations. We saw that the Tweety is a penguin, Polly has feather, Polly can fly, and most importantly, Tweety cannot fly. This contradicts with our theory in mind, because we know that Tweety is a penguin and thus a bird, and thus it should be able to fly. Now our theory is faulty, for it becomes incompatible with our latest benchmark observation, and we have to repair our faulty theory. In our previous work, we proposed such an ABC system to repair a faulty theory with a combination of abduction, belief revision, and conceptual change. The idea is simple. We fit the system with our theory and the observation as input. Then our system will detect whether the theory is faulty, maybe using resolution or forward chaining or backward chaining. If yes, then the system search for repairs iteratively until it detects no fault in the theory or cannot find any repairs. We also formally defined the notion of the observation. We call it preferred structure. That is, we prefer that to be true, and 2 types of fault. The preferred structure is comprised of 2 sets of axioms, the true set and the false set. We define that the fault-free Datalog theory should be able to infer all the axioms in the true set, or we say that the theory will be insufficient. And the fault-free Datalog theory should not be able to infer any axioms in a false set, or we would say that the theory is incompatible. So if you are in the theorem proving community or from the inductive logic programming community, you will find these definitions very familiar. We also defined 3 classes of repair operations: abduction, which can add an axiom into a theory or delete a precondition of a rule; belief revision, which can delete an axiom from the theory or add a precondition to a rule; and last but not least, conceptual change, which can modify the signature of a predicate. Here is the flying example for the ABC system. The input is the Datalog theory, and the observation is split into 2 sets, the true set and the false set in the preferred structure. The ABC system takes these 2 inputs and outputs a repaired fault-free theory. However, the fault-free repairs are not necessarily unique. And at each step, our ABC system can overproduce a lot of possible candidate repairs. For instance, we can easily find that such another repair of this faulty theory. Basically, this repair on the right just remove all the rules and copy the true set axioms to our theory. Now we have two repairs. So the problem is, which one shall we choose? Which one is better? I believe that most of us will prefer the left because by intuition, the right one entirely removes the vital rules, incurring a huge loss of information. But a further question is, how can we know how vital an axiom or a rule is? We will need a formal way to quantify how vital it is. And the main contribution of our work is to propose such a formal measure. We are not the first one to identify such a problem and try to solve it. Perhaps the epistemic entrenchment, that is an ordering of an axiom with respect to the importance, is the most well-known early work in this field. But Gardenford in 1988 only proposed such a set of postulates about how this ordering should be, but did not have a concrete computing method. But very soon, some quantitative measures emerged. These measurements only consider the unwanted consequences. That is, how many faults they will occur, and ignoring the wanted consequences. And Nikitina in 2012 and Urbanus in 2020 proposed some methods that measure the importance of an axiom by counting the number of both the wanted and unwanted consequences. That means the true consequence and the false consequence. We will take a further step, that is to count the number of the both wanted and unwanted proofs. So here is our solution. We propose a new measure to quantify the vitality of an axiom given the benchmark, or say the preferred structure. Our key insight is that a theory is better than another if it has fewer faults relative to its preferred structure. Or when two theories have the same number of faults, then the one that can establish more proofs for the true set axioms and fewer proofs to the false ones will be better. And then an axiom's vitality will be evaluated according to how much that axiom can support the preferred structure. I will demonstrate the idea by this one example. So for the axiom, Tweety has feather. In the true set, we need this clause, if bird then feather, to prove it. So this clause is vital for proving the true set axiom. But for this axiom, Polly can fly, we can directly prove it from this clause, Polly can fly in our theory. I know that Polly can fly because Polly can fly may sound a bit nonsense, but it can be a proof in formal logic. So this clause, Polly can fly, is vital for proving the true set theorem, Polly can fly. But it is not so vital because we can also establish another proof for this true set theorem. We can say that Polly can fly because it is a bird, and a bird can fly. Now we have two independent proofs, and they share no common axioms and rules. So the axioms used in these two proofs are both vital, but none of them are as vital as the previous rules if bird then feather. Among them, we will say that the rule, if bird then fly, is even less vital because it participates in a proof to a false set theorem. Tweety can fly because Tweety is a penguin and penguin is a bird and a bird can fly. Now you can see our intuition, and we formulated our heuristic idea like this. I'm not going to go through the math in this presentation. Okay. No, never mind. I'm not going to walk through the math. I just want to highlight that this math just highlight the simple idea that for an axiom in the theory, the more true set axioms depend on it, the more vital it is. And we tend to keep this theorem, or we tend to add it into our theory if it is not that in it. On the contrary, the more both such theorems depend on it, then the less vital it is, and we tend to modify it or simply drop it. And the same for the preconditions in a rule. So for a precondition of a rule in a theory, the more true such theorems depend on it, the more vital it is. And the more false such theorems depend on it, the less vital it is. That's all of our proposed benchmark-based vitality measure. Now I'm going to show the effectiveness and how effective the vitality measure is in helping to select the best repairs among the overwhelmingly many repair candidates. Formally speaking, we designed an empirical experiment to examine such a hypothesis. That is, selecting repairs based on vitality will prioritize the best repair theories. Here is our empirical design. So given a logical theory and its preferred structure, we invoke the repairing procedure. In our case, it's the ACS system. That it adopted our vitality definition to the output a set of repairs. And from the output repair theories, we identify the best ones by hand. Then we identify the changed axioms of the best repairs and the non-best repairs. Then we compute the vitality of these changed axioms and compare them. We expect that if the changed axioms of the best repairs are all those that of the least vitality, then our hypothesis gets supported. Here are our main results.
Okay, Ruiqi, 5 minutes.
Okay. Here are the main results. We conducted the experiment on 10 toy theories, and the most important indicator is the last column, saying that in these 10 experiments, the changed theorems of the best repairs are those of the least vitality. This is a strong evidence that our proposed vitality measure is effective in helping to select the best repair theories. For more details, you can go to our papers and have a look. So we also noticed several limitations in our work. We recognize that our the theories in our evaluation set is pretty small, so we need to do more. In the future, we need to do more sophisticated evaluations. And one fatal limitation may be our method only applicable for the Datalog theories, because we need the decidability. So here are some takeaway messages. We proposed a heuristic measure to quantify how vital an axiom is in a Datalog theory, and we empirically evaluate our vitality measure on and show that it performs well, but we need more sophisticated evaluation in the future. And last but not least, although we have focused on the implementation in our ACS system, we consider our approach as a solution for repair selection that are applicable to other automated theory repair systems. Okay, that's all. Thank you for your attention. Oh, no, only 2 minutes left.
We have time for 1 or 2 quick questions.
Yes.
Hi, yeah, this is Pat Langley. I heard a variant of this talk a few months ago from your first author. And at that time, I pointed out to her that there was a large body of work on repairing data log theories going back to the early 90s. And, and so I was hoping you would talk about them and how your approach differed. Are you familiar with Ray Mooney's work on this area?
I'm sorry. Actually, I'm new to this area. And
okay, well, so I'm going to forward you the email. But,
okay.
but basically, they start from an existing data log theory. Given training cases, they have operators for repairing that. They do heuristic search through the space. They have a different evaluation function for you, but otherwise, it's very, very similar, including the operators. I encourage you not to use the word benchmark driven. These are just data sets, right? There's no benchmark here. So benchmarks are evil. Don't use that term.
Okay. Well, it may be confusing. I'm sorry.
Thank you.
I should pick a more proper term.
Okay, thank you. So we'll proceed to the next paper, Adhar Gupta.